Binomial probabilities, they take a long time to get used to. It's a hard thing to wrap our brains around because of the way the formula is structured and that sort of thing. Here's what we have. If you have a binomial probability, just the very term means there's two terms. We could describe things as being successes and failures. It doesn't mean there's only two simple events. You could take the 6 outcomes of a die and make it binomial. You can say, hey, rolling a 1 is a success, rolling a 2 through a 6 is a failure. So as long as you can categorize, so you have this is a success and this is a failure, it's fine. N has to be fixed. N is the number of trials. So you have to know going in, like if we're rolling a die, we're going to roll the die 7 times. That's it. No more, no less. So in the problem, N has to be fixed going in. The trials have to be independent of one another. So flipping a coin, rolling a die, doing a roulette wheel, whatever. The one event doesn't affect the other, so the events are independent of each other. The trials, I should say, are independent of each other. And because they're independent, that implies that the probability P stays fixed. And P is the probability of a success. It's a success rate. It is a proportion. When we do inference on proportions, this is what a proportion is. It's a success rate for any one trial. But at any rate, these are the 4 things it takes to have a binomial setting and be considered a binomial. On the AP exam, I tell my students, any probability situation, determine the number of trials going in. When you're having more than one trial, the word and means multiply. And usually, you guys, if you're seeing a problem on an AP exam, and you have anywhere between, let's say, 3 and 12 trials, you're probably looking at a binomial probability situation. And so I tell my students, rule out binomial for small sample probability situations before anything else. See if you can identify N and P in the problem, and if you can and P stays locked in, you're almost certainly looking at a binomial situation. It's a pretty practical probability situation, and AP is going to test you on it because it is so important. Let's suppose that 85% of Americans can swim. And let's suppose, actually, we're going to compare adults to kids. Then would we be doing a pooled PHAT? I don't know. It's interesting. And what if an old couple, George and Gladys, finally, they owned a lap dog and they decided to get off their butts and learn how to swim? They might threaten their dog and say, oh, now you're really going to learn what it means to be a lap dog and you're going with us. So anyways, but I'm going to resist the urge to try too hard and interject humor on this video, so I'm not going to bring all that up. Anyways, let's suppose we have a sample size of 5, and we want to find the probability that 3 out of the 5 Americans we select can swim. Well, we go over here. Don't look at that. Look over here. Look at this. Let's suppose the first 3 people we randomly selected can swim, and the next 2 can't. So 3 successes followed by 2 failures. Well, since we're selecting more than one thing, the word and means multiply. So we got a swimmer and a swimmer and a swimmer and a person who can't and a person who can't. So we multiply those together, which means we have 0.85 to the 3rd power, the success rate to the 3rd power, times the failure rate to the 2nd power. Now that's not the only way we can end up with 3 swimmers out of 5 who can swim. So if we wanted to, we could start to write down all the possible outcomes for getting 3 swimmers and 2 non-swimmers in a group of 5. But the nerd is telling us, don't do that, that's working too hard. We can use the binomial probability formula. So this Hummer is on the formula sheet, the 2nd page, where all the formulas for probabilities are in the AP exam. And this one says the probability that the random variable x in the binomial setting, in a binomial distribution, the random variable x is the number of successes that we could get. And in the world of math and science, when we see K or we see C, usually they're constants, and they are here. We're saying you're trying to find the probability that X, the number of successes, equals the stipulated number of successes in the problem. Like for ours, it's 3. Hey, what's probably get 3 successes? It's a combination of N choose K, and that's all the formula sheet will tell you, but you're going to need to understand how to show and calculate a combination formula, which is right here. You at least have to be able to show it, because on a multiple choice question, you have to be able to identify what that is. So at any rate, the formula is the number of combinations times the success rate to the number of successes times the failure rate to the number of failures. So let's just take a look at this and see why this makes sense. In our problem, the probability of getting 3 successes in a sample of 5, this part of the formula counts the number of combinations, the number of ways that you can end up with 3 out of the 5 people selected being swimmers, and then that gets multiplied by this, which is the probability of getting 3 successes and 2 failures in any of these situations. Because no matter which persons we selected were the 3 who could swim or the 2 that could not swim, in the end, the probability of getting 3 swimmers and 2 non-swimmers is going to be the success rate to the third and the failure rate to the second. So if you put all this together, this formula makes a lot of sense. For each combination, this is the probability of getting 3 swimmers out of 5, and this multiplies it by the number of combinations, the number of ways that you can end up with 3 of the 5 people being swimmers. So the binomial probability formula makes sense. If you go further into class, obviously you learn how to do binomial PDF and CDF on the calculator. For the sake of getting ready for the AP exam, outside of the practicality of it, you don't often have to spend too much time doing that, although it does save you time here. So actually I'm not going to argue that the binomial PDF will save time, but we're not going to cover it right now. You can ask your teacher how to use that. Let's suppose that 95% of dogs can swim. Like a moment of silence for Skippy. I didn't know. I assumed that all dogs could swim. I didn't know. God rest his soul. Anyways, we have an SRS of 8 dogs. So we're going to take 8 dogs at random. Find the probability that 7 dogs are swimming. So 7 dogs are swimming, 6 geese laying. I don't know what the other animals are doing, but 7 of these 8 dogs, they're swimming. So what we're going to do is we're going to do a binomial probability formula. We're going to say, okay, the probability that out of 8 dogs we get 7 that can swim is equal to 8 factorial over 8 minus 7, which is 1 factorial times 7 factorial. By the way, if you ever get to a situation where you get 0 factorial in a formula, by definition it equals 1, so it's no problem. Anyways, this counts the number of ways that 7 out of the 8 dogs could be swimmers, and then we're going to multiply it by the probability that any one dog is a swimmer raised to the 7th power, because we're looking for the probability of 7 successes, and we have 1 failure. We'll call it Skippy, I don't know. And so anyways, if you multiply all that through, you get your answer. And again, we could go, we really should, we could go to binomial PDF, and you're going to type in N, P, and X in alphabetical order. The number of trials, the success rate, and the number of successes in alphabetical order. So you type in N is 8, P is 0.95, and X is 7, hit enter, and it will give you that probability. If we said, okay, in this same scenario, what's probably get at least 1 dog that can swim, we say, hey, wait a minute, look at there, woohoo, at least 1. I know what to do. If we watch the basic probability video, or you know your stats well enough and your probability good enough, when you see the probability of at least 1, it is much quicker to say, I'm going to find the probability that we get no dogs that can swim, no swimmers out of 8, and I will do 1 minus that probability right there. There's 2 ways to get that. You could use the binomial formula. You could use binomial PDF. I'd rather that you recognize the fact that if you get no dogs that can swim, there's only 1 way that can happen. You don't need to multiply by the number of combinations, because if none of the 8 dogs can swim, then it's not a swimmer and not a swimmer and not a swimmer. So your probability would be 1 minus 0.05 to the 8th power, because all 8 dogs can't swim. So if you see that, that's wonderful. If not, you can use the binomial probability formula and put 0 successes in or whatever. And then finally, if the last question might be, what's probably getting 7 or 8 dogs that can swim? This might be a realistic question on an AP exam, and they'll want you to show this probability right here for 7 successes, plus the probability that you get 8 successes, either written again as the probability formula, the binomial probability formula, where it's 8 factorial over 0 factorial times 8 factorial times 0.9 to the 8th times 0.05 to the 0 power. So it could be these 2 things added together. But a more sophisticated approach would be to say there's only 1 way you can end up with 8 dogs that can swim out of 8 dogs, and this guy right here equals 1, and anything raised to the 0 power is equal to 1. So really, the only way to come up with, or the quickest way to come up with 8 dogs that can swim is simply to multiply 0.95 to the 8th power. So the answer to this would be the probability of 7 successes plus the probability of 8 successes. So just be comfortable with that. That's a quick rundown of binomial probabilities. Good luck.